Hi, this lecture is to find the frequency response of an FIR filter. The main reason to filter a signal is to reduce and smooth out high frequency noise associated with a measurement. Ideally, frequency response characteristic of analog filters like ideal low pass filter, high pass filter, band pass filter, and band stop analog filters, as shown here in this figure. To explain it, let's just look at the spectrum of each one. The first one is a low pass filter. In this low pass filter, you'll observe in the spectrum that it's almost equal to 1 from 0 up to omega c. What's omega c? Omega c, it's called the cutoff frequency. What does it mean, the cutoff frequency in low pass filter? It means if you have any signal and this signal has many components with different frequencies and you are interested to pass certain frequencies from 0 up to omega c. As an example, if omega c is equal 10 radian per second, so it means that all components that have frequencies between 0 and 10 radian per second will pass, and beyond that, or any frequency higher than 10 will not pass. It will be stopped. So that's why we call it low pass filter. For high pass filter will be the opposite. Any frequency above the cutoff frequency will pass, but anything beyond that will not pass. That's why we call it high pass filter. For band pass filter, if you have two frequencies, let's say that's 20 radian per second and 50 radian per second. So in band pass filter, it will pass only the frequencies between 20 and 50, and below omega 1 or below 20, it will not pass, and above 50 or above omega 2 will not pass. Band stop filter, let's say take the same number here, like 20 radian per second and 50 radian per second. It means that if you have any component with frequencies between omega 1 and omega 2, i.e. between 20 and 50, will not pass, will be stopped. However, anything below 20 will pass and anything above 50 will pass. So that's the band pass filter. So in general, these are the basic four filters in general. Well, there are many types. They can be classified according to the way that operate, or maybe according to the components they are used. So maybe you'll find that they have analog filter. And analog filters, it means that the filters you are using analog components. And also you can find digital filter. And in digital filters, digital component will be used, or maybe it will be like in a form of software. One of the most important applications for digital signal processing in communication equipment is filtering. Digital filters allows the selection of the desired signal and rejection of noise. We are going to focus on one filter called FIR. What does it mean, FIR? F stands for finite, I stand for impulse, and R stand for response. So this type of filter, it means if you put in an impulse, that's a single one sample, followed by many zero samples, will come out after the one sample has made its way through the delay line of the filter. A linear time filter consists of three building blocks only: additions, multiplication, and delays. These three blocks, the first one, addition, it will look like that. It means if you have two signal, let's say x1 and x2, then you will get the sum. Multiplication or amplification, it will look like that. If you have signal x, it will be, and this one has amplification called h, So the output will be h times x. And another one, the delay. The delay will be like that, represented by z minus 1. If you have x of n, it will be delayed by 1 unit only, will be x in minus 1. If you have z minus 2, will be z in minus 2, and so on. So only z minus 1, it make delay by only 1 unit, be n minus 1. So if you look at the block diagram for FIR, it will look like that. Let's check how it operates. The first signal here at the input, it's x of n, instant n. So it will go to the amplifier or h naught. So the output will be x of n. Let's write x of n like that, times h naught. And then the signal will go to the delay element z minus 1. So here will be the output, the same x of n, but delayed by 1 unit, will be xn minus 1. And then it will be multiplied by h1. So you have here h1 xn minus 1. And then you add them. So you got here the sum, this signal and this signal, h naught xn plus this signal plus h1 xn minus 1. Let's follow. This signal xn minus 1, when it enters the time delay unit xz minus 1, it will be delayed another unit. So the output here will be xn minus 2. And this signal will go to the amplification gain here h2. So it will be h2 xn minus 2. And then it will be added to the previous signals. So you add another one here, will be h2 xn minus 2, and so on. You continue up to all stages in this block diagram. So let's just write, the sum till you get the output, because in the end you will have the output y of n. So how we write the output here? Let's just write what we did in this block diagram for FIR filter. Y of n will be equal the first element h naught x of n. I'm sorry, that should be written as small letter, x of n. And then h1 x delayed by 1 unit, h2 and x delayed by 2 units. And then you continue up to the last one, will be h, let's say m capital, times x, n delayed by m capital. Great. So what we do next? Right. Next, we use z transform to transform the whole equation. So for y of n, z transform will be y capital, y of z. And this element, you will have h naught and x of z. Plus, second element, h1. What about x n minus 1? It's x of z, and when you have delay, it will be multiplied by z minus 1 according to the properties of z transform. Let's take the second element, h2 xn minus 2. h2, it's a constant, and xn minus 2 will be delayed z minus 2 x of z. And you continue up to the last element. This element will be hm z minus m x of z. Now we'll take x of z common factor from all terms. So y of z will be equal to h naught plus h1 z minus 1 plus h2 z minus 2 up to hm z minus m, and all multiplied by the common factor x of z. So we know that h of z is equal to y of z divided by x of z, which will be that. So h of z will be equal h naught. You can make it in sum, as a sum, You can write this h n multiplied by z power minus n. See this term, hm z minus m. Well, if you like to change this one to use different index, that's okay. Like you can write h of m small, z minus m small, and m start from 0 up to m capital. That will be the transfer function. So that's our result. The transfer function in z domain equal to the sum from m equals 0 up to m capital, h of m, z power minus m. That's in z transform. All right. Remember, h of m here, you can write it like it starts by h0, h1, h2 by itself till up hm. We call this impulse response of the filter, which are just constant here in this case. Well, how to find the frequency response? To find the frequency response, you just replace z by e to the power of j omega. And since we are dealing with discrete, we are going to use this omega as we used before in Fourier transform for discrete time signal. So that's what I'm going to do. I'm going to replace in this expression z by e to the power j omega, and that will represent the frequency. So we'll write h of e to the power of j omega equal the sum m equals 0 up to m capital, h of m, pulse response, times z minus, let me write just minus m. I'm going now to replace z by e to the power of j omega. So e power j omega power minus m. And you know, when you do the power for an exponential expression, you multiply this minus m by the whole power. So you can write it equal to, from m0 to m capital, hm e to the power minus j m omega. And that will be the response, frequency response of FIR filter. Of course, that in general is a complex variable. And since the complex, it can have magnitude and the magnitude function of the frequency omega, and angle function also of the frequency. How you find the magnitude? The magnitude, you'll find it by find the absolute value of the function h, and the angle, you find the angle of the whole h. So you can write in the end h omega is equal to the magnitude times the angle, and all they are function of omega. That will be the final one. Let's just take a numerical example to see how can we implement it. Let's say that you have FIR filter, and its impulse response defined as 1, 1, 3, 1, 1. And put a line here. That means that's the first element, h of 0, h of 1, h of 2, 3, 4. So the last one will be h of 4. So it means our m is equal to 4. So if you write the impulse response, h, it will be h small. If we talk about impulse response, h small of n, you can write h naught, h1, h2, h3, h4, right? If you are going to convert that to frequency response, we are going to use what we got just here. This is the frequency response. Okay, let's write the expression and substitute. H aj omega, or omega, is equal to the sum from m equals 0 to m capital, and m capital is equal 4 in this case, from m0 to m capital, which is equal to 4, and hm e to the power minus j omega m. We know that hm given 1, 1, 3, 1, 1. So you will write h0, which is equal to 1, m time e power minus j omega m, and m is equal to 0, so it'll be times e to the power of minus j0. The second element, when m, that's we got it when m equal to 0. When m equal to 1, so you'll have h of 1, and h of 1 is equal 1 is in the example. So 1 times e to the power of minus j, but m equal to 1 in this equation, so be minus omega. All right. Then you go for m equal 2. When m equal 2, h was equal 3. Okay, these numbers I put it there, 1, 1, 3, they are the value of h. This is the value of h0. That's the value of h1. That's the value of h2. E to the power minus j2 omega. Still have another 2 plus. After 3, it was 1. That's h of 3. E to the power minus j3 omega. Plus, the last one was also equal to 1. E to the power minus j4 omega. That's h of 4. So that would be the series, you know. Well, let's look at, in a neat way, simplify. It would be like 1 plus e to the power of minus j omega plus 3e minus j2 omega plus e minus j3 omega plus e minus j4 omega. In this case, you got it. You found it already. But if you like to simplify it, what I'm doing now, I'm going to do math. But this is here up to here, you did a good job. It's the right result in a complex form. You can simplify. To simplify this, I'm going to take here. The highest one is e to the power minus j4 omega. I'll take its half, so j2 omega. I take it as a common factor, and let's see what we got here. This one, so it means it has to be multiplied by the positive, because when you multiply this, a g2 omega by a minus j omega, be a power 0 b1. All right, plus that a minus j omega, and you took here minus 2, so you have to add only 1, so to be like e to the power of j omega plus 3, that's minus 2 omega minus omega, nothing, be constant, plus e minus j omega, so you have to multiply by e minus j omega. To check, you multiply this by this, you add the power. That's right, e power minus j to omega. So that's what we got. We are going now just to rearrange. It's just simple algebra. And I will try to find this term. Let's just take different color here. We'll take this term a to the power of j2 omega and a to the power of minus j2 omega. It will make like a cosine, right? So let's do that. I'll take it together, j2 omega plus, I'm just trying to collect terms that will help me to simplify. And you have e to the power of j omega, e to the minus j omega. I take it together, e to the power j omega plus e to the power minus j omega. And 3 left, that's all. All right, now it looks simple and obvious. That will be a common factor. Then you have e to the power j2 omega plus e to the minus omega. That will give you, if you divide by 2, be cosine, you don't have, so you have 2 cosine 2 omega. All right, and this term will be 2 times cosine omega, and that's a fixed term, you see. So that will be the frequency response. And if you want to check, you can calculate it or use a program. You want to find the magnitude, so you just you take the magnitude, the absolute value of this value, what you have here. So actually all this magnitude doesn't have an angle, and this one, the magnitude of e to the power of any minus j is equal 1 because it's only angle, right? So always the magnitude of e to the power minus j complex number, that will be always 1. So the magnitude will be equal to cosine 2 omega plus 2 cosine omega plus 3. That's the magnitude. If you want to find the angle, so the angle is function of omega also. You want the angle of this one and the angle of this one. All right. So when you look at it, you will find the angle only here because this is like constant, doesn't have angle. So the angle of this one will be the power if you remove the j. So you have minus 2 omega. Right? So this will be the angle. You told me what is the angle of this part? No, it doesn't have angle. It's like, I mean, when you write something like that, say 4a to the minus j pi over 2, for example. So I ask you, what is the angle of this one? The angle of this one is 0, and the angle of this one is minus pi over 2, and then when you multiply, you add the angle. So in the end, you will get minus pi over 2. So that's what I did exactly. I found the angle here, and the angle here is 0, so I added it to get minus 2 omega. So that will be the magnitude and the angle of the frequency response of a FIR system. All right, thank you.